Hello, I am Dr. TzuEn Lin. In this video, I would like to present applications of scanning electrochemical microscopy, in abbreviation SECM, on investigating catalysts. This is part 1. In this part, I would like to explain the basic principles of SECM and its operation modes, so that you will have some ideas about how SECM works. This video is composed of several different sections. In the first section, a short history of SECM will be described. And then I will let you understand the basic principles of SECM. According to your experiment and your purpose of study, different operation modes can be chosen. So we need to understand different operation modes and how it works. Finally, we will have a brief summary. The story of SECM begins in 1989 when two electrochemists, Alan Bird and Royce Armstrong, invented SECM. After 2 decades, more than 1,800 peer-reviewed papers have been published, including several reviews. SECM belongs to scanning probe microscopy family. The ancestor of SPM is profilometry. It provides the information of one-dimensional topography. For example, atomic force microscope (AFM) is evolved from profilometry. The other type of SPM is scanning tunneling microscope (STM). It inspired the invention of SECM, and a large number of variants of scanning electrical probes were invented as well. In scanning probe technique, a sharp tip interacts with the sample surface for data collection. The relative tip in location over the sample can be changed in XYZ direction. The sequential data collection procedure is done during the scanning, and the sample-probe interaction is recorded as a function of probe location and other parameters. The image is reconstructed from the measured signal or after data processing. So how does SECM image work? The image is reconstructed from measured signal. In SECM, the probe is a microelectrode or nanoelectrode. For instance, you have a flat sample with 3 active sites marked in red and 3 non-active sites marked in white. The probe will do light scan over one direction and then move to another line next to it to do another light scan. In the end, you will get the pixel image like this. If you collect more data, you can reconstruct a very nice image with high quality. In the second part, the basic principles of SECM will be explained clearly. SECM is a tool to detect the local electrochemical reactivity of a sample surface. So first, you have a probe, which is usually microelectrode, and then you have a sample. To sense the specimen, usually the current signal is measured Of course, you can measure potential signal as well. Then the sample can be interact with the probe by sample-probe interaction. Finally, the information of the sample surface reactivity can be understood. So how does SECM measure the sample surface activity? For example, you have an active substrate which can oxidize the redox mediator into oxidized form. You can put one electrode near the sample substrate surface. Once you apply a suitable potential, the following reaction occurs. The oxidized species is reduced to reduced species. So in this way, you can measure the current, and depending on the increasing current, you will know the activity of the sample substrate surface. The probe of SECM is a microelectrode. Conventionally, a microelectrode is made of platinum wire embedded in glass insulator. The radius of the platinum wire is A. The radius of the glass insulator is R. The diffusion near the microelectrode can be described by fixed law. So C is the concentration of redox mediator. T is time. D is the diffusion coefficient. A hemispherical diffusion will be observed in this case. So that means if you apply a certain potential, a steady-state current can be measured. The steady-state current can be described by the following equation. The current equals to 4 DAC bulk. So that means the steady-state current you can measure is a constant. Cyclic voltammetry, in abbreviation CV, is a method to characterize microelectrode. In this method, a potential sweep will be performed, such as the plot on your left-hand side. On your right-hand side, this is a typical CV from a microelectrode inside ferrocimethanool solution. The x-axis is the potential you applied. The y-axis is the current that you measured. SECM experiments are performed in steady-state systems, which means a fixed potential will be used. In this case, 0.4 volt will be used, and in bulk solution, a constant current will be measured. In the third part, different SECM operation modes will be explained. It's very important that you choose the correct operation mode during the experiment. The basic setup of SECM is like this. A probe is connected to a positioning system which can move into XYZ direction, so that the probe can scan over the sample surface, or approach to the sample surface vertically. A potential state is required to control the potential between the working electrode and reference electrode. The counter electrode is also required. So all the system is immersed in an electrolyte solution. So in the first mode, the probe is approaching to an insulator, and the reduced species R. The diffusion of it is hindered, and therefore the current signal decreases. In this mode, it is called negative feedback mode. In the second situation, the probe is approaching to a conductor, so the conductor can regenerate the redox mediator. In this case, the current signal increases. So this case is called positive feedback mode. In the third case, the analyte R is not presented in the solution at the beginning, so the generator generates the R during this process. When the probe is approaching to it, the current signal increases. In this mode, it is called generation collection. Let's have a close look inside negative feedback mode. So when a probe is placed in bulk solution, the diffusion pattern of R is hemispherical. While the probe is approaching to an inert surface, such as an insulator, the diffusion of R is hindered. So if you plot the normalized distance versus the current that you measure, such as the plot at your right-hand side, the current decreases as the distance decreases. So in this case, by using SECM, you can understand the topography of the sample surface by using negative feedback mode. So let's have a close look into positive feedback mode. As I just mentioned before, in bulk solution, the diffusion of R is hemispherical. If the probe is approaching to a conductor or an active surface, the R can be regenerated by the substrate, and therefore, at your right-hand side, the approach curve of a positive feedback mode is like this. The current increases drastically when the probe is approaching to the sample surface. And therefore, in this mode, you can measure the kinetic information of the sample substrate surface. The information of approach curve is very important. The kinetics of electrochemical reaction can be obtained by using approach curve fitting. As you can see that there are many complex equations, but actually it's very simple. You just put the parameter and then the activity of the sample surface in positive feedback mode or negative feedback mode can be obtained. The probe of SECM is very sensitive to microenvironment. In this figure, it illustrates several different kinds of situations. As I just mentioned before, if the probe is placed in the bulk solution, the hemispherical diffusion can be observed. If the probe scans over an active site and non-active site, the current over the active site will be higher than the current over the inert surface. The current response is very sensitive to the distance between the probe and the substrate. Therefore, if a probe is scanning over a sample surface which has topographical features, the current will be different. In the final cases, the probe can be used to study the ionic current or the flow of the electroactive species over the nanopore or permeable membrane. SECM is a powerful tool that can create micro or nanostructures. For instance, the metal deposition can be achieved. The dissolution occurs at the surface of the crystal. In another case, SECM can generate Brownian gas and therefore passivate the film. The surface modification can also be achieved by click chemistry. So this is why that SECM is different from other tools, because it can change the surface property. So now you understand the basic principles of SECM, and you saw several examples of its application. The summary is that if you take the electro SEI, you can see the new world by electrochemistry. So SECM can measure the kinetics of interfaces between solid-liquid, gas-liquid, and liquid-liquid. High-resolution image of chemical reactivity can be achieved by SECM. And surface modification can be made by SECM as well. Finally, SECM can be integrated with microfluidic system or other types of scanning probe techniques, such as SECM and AFM. Thank you for your attention.